To hover a drone, you have to satisfy a basic aerodynamic requirement. You must generate enough upward lift by displacing air downwards to perfectly balance the physical weight of the machine. But the moment you spin a propeller to create that lift, you run into Newton's third law. Every action has an equal and opposite reaction. As the motor applies torque to spin the blade pushes back with an equal amount of force. If you only had one propeller, this opposing force would spin the entire body of the drone out of control. This diagram shows the mechanical solution. By having diagonal pairs spin in opposite directions, clockwise and counterclockwise, the reactive torques cancel each other out. But as these lower diagrams outline, moving requires deliberately breaking that balance by altering specific motor speeds to shift the thrust vectors. Managing 4 independent thrust vectors simultaneously against gravity, changing air density, and wind requires constant, rapid mathematical adjustments. A human pilot manually adjusting 4 separate throttles simply cannot process the physics fast enough to keep the machine upright. Because human reflexes are too slow, a drone relies entirely on a continuous, high-speed conversation between its digital brain and its physical motors to avoid falling out of the sky. Imagine a sudden gust of wind tilts the drone to the left. The airframe physically shifts, and that unwanted movement is instantly detected by a sensor chip called the Inertial Measurement Unit, or IMU. Inside the IMU are microscopic moving parts, MEMS gyroscopes and accelerometers. They measure the exact angle of the tilt and the acceleration of the disruption, feeding that raw physical data straight into the drone's flight controller. This graph illustrates how the flight controller processes that data using a PID algorithm: proportional, integral, and derivative. The algorithm calculates the exact mathematical counterthrust needed to level the drone out, smoothing the error into a stable line without overcompensating and causing a crash. At this stage, the flight controller knows exactly what physical action needs to happen, but it is just a microprocessor. It cannot generate physical force. It can only output a digital command. In this schematic, you can see how that digital command travels. It hits the electronic speed controller, or ESC. The ESC acts as a translator, reading the digital request from the flight controller and dispensing raw electrical current from the battery to specific motors. In a fraction of a millisecond, the drone has measured a physical disruption, processed it through a mathematical algorithm, and generated a targeted electrical command ready for mechanical execution. That current flows into brushless DC motors. Unlike traditional motors, they lack physical brushes rubbing against an internal commutator. By eliminating that physical friction, these motors can change their speeds almost instantaneously. The ESC uses electronic commutation, rapidly switching a 3-phase current through the motor's copper coils to create a sequential magnetic circle. The rotor's permanent magnets chase this rotating field. Increasing the current's frequency spins the field faster, generating massive torque without mechanical wear. As the motor spins faster, the propeller's RPM increases, displacing more air downward. This generates the precise corrective lift calculated by the flight controller. This detailed waveform plot reveals the microscopic timescale of this sequence. There's a delay of just 0.0015 seconds between the control loop sending a command and the electrical current hitting the motor. A quadcopter's steady hover is maintained by an aggressive, high-speed physical reaction to thousands of microscopic electrical pulses every second. The quadcopter operates as a continuous, high-frequency feedback loop that actively resists gravity to maintain its position. Because this loop of sensing, calculating, and translating current into thrust is so efficient, engineers can scale the physical airframe for heavy industrial uses without altering the underlying logic. We see this scaling in fixed-wing drones mapping terrain and massive hybrid VTOLs lifting off vertically before transitioning to forward flight to navigate harsh environments. Whether it is a palm-sized racing drone navigating a tight obstacle course or a heavy-duty commercial carrier transporting medical supplies, they both rely on the exact same signal-to-thrust journey. A drone holding its position demonstrates the tight integration of its systems, a cycle where software logic, electromagnetic pulses, and air displacement align to keep the airframe stable.